We are now starting the last module, module 5 of chapter 7. In the last module, we have defined 4 types of derivatives of a function, and we have shown that for a non-decreasing function f on closed interval a b, all the 4 derivatives exist almost everywhere in closed interval a b finitely. In this module, we are going to prove one of the most important results of real analysis. We are going to show that a monotonically increasing function is actually differentiable almost everywhere in closed interval a b. The proof is quite tough, and we will try to proceed very slowly and see the logic behind the proof, and we will consider only this particular result during the presentation of this module. So, we present one of the main results of chapter 7, and of course, the main result of this module which we are going to prove. The result states that if f is a non-decreasing real valued function on closed interval a b, then f is differentiable almost everywhere on closed interval a b. Recall that we know that being a non-decreasing function, f has at most countable number of discontinuities, and so we already know that f is continuous almost everywhere, and that particular proof is not that much tough. It is quite an easy observation, taking into account the oscillation of the functions and the fact that all the discontinuity points of f are jump discontinuities. But this particular result is not at all trivial, and the proof is one of the most difficult proofs in real analysis. So, let us start our journey. So, first observe that for f to be differentiable at a point, all the 4 derivatives should be equal. So, we have to show that all the 4 derivatives of f are equal almost everywhere in closed interval a b. Recall that we have already shown that all the 4 derivatives exist finitely almost everywhere in closed interval a b. So, we will show that d upper plus f x equal to d lower plus f x holds almost everywhere. The other result will follow similarly. We will not go into the details of that proof. From the definition, it is evident that d upper plus f x is greater or equal to d lower plus f x at all points x belonging to closed interval a p, because d upper plus f x is the lim sup and d lower plus f x is the lim inf of the same set of real numbers. So, let us consider the set capital A as the collection of all x belonging to closed interval a b, where d lower plus f x is strictly less than d upper plus f x. So, if we can show that mu star of A is equal to 0, then evidently we will have the result that on the complement of this set capital A, d upper plus f x equal to d lower plus f x, and this will prove our assertion. On the contrary, if possible, suppose that mu star of A is greater than 0. Now, see that if we consider for two rational numbers p and q, where q is greater than p, the collection of points x belonging to closed interval a b, where d lower plus f x is less than p, less than q, less than d upper plus f x. Observe that since the set of rational numbers is dense in the set of real numbers, so when for a point x we have d lower plus f x less than d upper plus f x, we can always find first a rational number p with the property that d lower plus f x less than p less than d upper plus f x, and we can find again another rational number q with the property that p less than q less than d upper plus f x. And consequently, the set capital A can be written as the countable union of all these types of sets, that is union small p belonging to capital Q, union small q greater than small p, where small q again is a rational number belonging to capital Q, collection of all x belonging to closed interval a b, where d lower plus f x is less than p less than q less than d upper plus f x. So, from the countable sub-additivity of the Lebesgue outer measure mu star, it follows that there exist two rational numbers p 0 q 0 such that from the above formulation of the set capital A, we have mu star of A is less or equal to sum of the measures of all the sets of the form x belonging to closed interval a b, where d lower plus f x less than p less than q less than d upper plus f x. As the mu star A is strictly greater than 0. So, this shows that the sum of the series on the right hand side should be greater than 0, and consequently, we have this particular observation that for two rational numbers p 0 q 0, the set capital B so constructed must have positive outer measure. So, suppose that mu star capital B is equal to alpha, which is greater than 0. Now, let epsilon greater than 0 be given. From the definition of outer measure, we can find an open set capital G containing B such that mu G is less than alpha plus epsilon. Without any loss of generality, we can further assume that G is subset of open interval a b. Now, from the definition of d lower plus, for each x belonging to the set capital B and for each positive integer k belonging to capital N, we can choose a sequence of points y x k, k belonging to N, such that x less than y x k, this is less than x plus 1 by k, and where the interval closed x y x k is subset of G, and this is true for all k belonging to capital N. Now, observe that for this particular choice of points, we have f of y x n minus f x by y x n minus x less than the number p 0. Now, again we consider the collection of all closed intervals of the form closed x y x k, where x runs over the set capital B and small k runs over all natural numbers. See that from the definition of D lower plus, for each small positive number we can get such an interval whose length is less than the specified small number, and obviously each interval x y x k contains the point x. And so, this particular collection of closed intervals closed x y x k covers the set capital B in the sense of Vitali. So, again we can apply the Vitali covering theorem, and by Vitali covering theorem we can find a finite collection of mutually disjoint closed intervals from this collection, say x r y r, where one less or equal to r less or equal to capital M, such that mu star of B minus union r equal to 1 to capital M closed x r y r, this is less than epsilon. Consequently, we have sigma r equal to 1 to capital M f y r minus f x r, this is less than sigma r equal to 1 to capital M p 0 into y r minus x r, and this is again less than p 0 into measure of g, as all the intervals x r y r are contained in g, and this is again less than p 0 into alpha plus epsilon, since mu g is less than alpha plus epsilon. Now, let us define the set capital C as the set capital B intersection whole union r is equal to 1 to capital M open x r y r. Now, we have mu star B which is equal to alpha, this is less or equal to mu star C plus mu star B minus C by the subadditivity property of Lebesgue-Outer measure. This is again less than mu star C plus epsilon, and consequently we get mu star C greater than alpha minus epsilon. Now, we use the definition of D upper plus, and using the definition of D upper plus for each z belonging to C and for each positive integer k, we can choose a sequence of points w j k, k belonging to capital N, which has this property that z less than w z k less than z plus 1 over k, and the closed interval z w z k is chosen so small that it is contained in open interval x r y r for some r. We can always choose the interval small enough, because we have the limit property of D plus from the definition. F of w z k minus f z by w z k minus z, this ratio is greater than q 0. Again, as before, the collection of closed intervals z w j k, where z runs over C and k belongs to capital N, covered the set capital C in the sense of Vitali. So, applying Vitali covering theorem, again we can find a finite collection of mutually disjoint closed intervals. From this collection, say Z S W S, where 1 less or equal to S less or equal to capital N, such that mu star union S is equal to 1 to capital N Z S W S, this is greater than mu star C minus epsilon. And consequently, in this case we have sigma S is equal to 1 to capital N f of W s minus f of Z s. This is greater than sigma S is equal to 1 to capital N q 0 into W s minus Z s. This is again greater than q 0 into mu star C minus epsilon. The right hand side is again greater than q 0 into alpha minus 2 epsilon. Now, for each r 1 less or equal to r less or equal to capital M, let us set dr as the collection of all those positive integers small s, for which the closed interval Z s W s is subset of open interval x r y r. Since the function f by our assumption is non decreasing, so we finally get q 0 into alpha minus 2 epsilon. This is by our equation less than sigma S is equal to 1 to capital N f W s minus f Z s. We can rewrite this sum as sigma r equal to 1 to capital M sigma S belonging to capital dr f W s minus f Z s, and this is again less or equal to sigma r equal to 1 to capital M f y r minus f x r, and we have already shown that the right hand side is less than p 0 into alpha plus epsilon. Now, observe that we have got this particular relation, that q 0 into alpha minus 2 epsilon is less than p 0 into alpha plus epsilon. This is true for any epsilon greater than 0, which implies that q 0 alpha less or equal to p 0 alpha, and since alpha is a strictly positive number, so we can cancel it from both sides, and we have q 0 less or equal to p 0, which is not possible, as by our assumption q 0 is greater than p 0. And this proves that if we assume that the particular set capital A has positive Lebesgue measure, then we get a contradiction, and this shows that all the derivatives must be equal and must exist almost everywhere on the whole set, and this proves our assertion. So, we have shown that for a non-decreasing function f defined on closed interval a b, f is differentiable almost everywhere in closed interval a b. Now, recall that when we consider a function of bounded variation on closed interval a b, that function of bounded variation can be expressed as the difference of two monotonically increasing functions. Now, since each of these component functions, monotonically increasing functions, are differentiable almost everywhere in closed interval a b, so the function of bounded variation is also differentiable almost everywhere in closed interval a b. The same is true for absolutely continuous functions also, because we have already seen that a function which is absolutely continuous on closed interval a b is also a function of bounded variation on closed interval a b, and consequently it can also be expressed as the difference of two non-decreasing functions. Again, coming to the derivatives of a function, we can actually show that if f is a measurable function on closed interval a b, then all its four derivatives are also measurable. We will not present the proof in the slide, the proof is given in the chapter. So, to summarize, what we did in the last module of chapter 7 is that we have proved a very important theorem showing that for a non-decreasing function on closed interval a b, it is differentiable almost everywhere in closed interval a b, and consequently this observation holds for functions of bounded variations as well as for absolutely continuous functions also defined on closed interval a b. And with this we finish this module.